Hello everyone, welcome to the Hitchhiker's Guide to CLIs in Python. I'm Vinayak, a software engineer currently living in New Delhi. I maintain Camelot and Excalibur, two tools that can help you extract tabular data from PDF files. Right now I'm in the Fall 1 batch at the Recurse Center, which is a self-directed educational retreat for programmers in New York City. If you're looking for a software/data engineer to join your team, do reach out. Let's get back to the talk. In the beginning was the command line. Well, not quite the command line we know today. They were typewriters, and we were communicating using Morse code. So one fine day, someone had an idea to connect a typewriter to an existing set of communication wires, and the Teletypewriter was born. Teletypes removed the need for an operator to know Morse code and reduced message typing speed and delivery time, which made it possible for messages to be flashed across the country with little manual intervention. Meanwhile, computers were becoming powerful enough to multitask and interact with users in real time, in contrast to the earlier batch processing model. So another fine day, someone had another idea to connect a teletype to a modem, which would let them interact with computers remotely. Among these teletypes was the Friden Flexowriter. In the Teletype Model 33, teletypes like these were adapted to provide a user interface to early computers, and this was the origin of the command-line interface. Users typed commands after a prompt character was printed on paper. After they were satisfied with the input, they would press enter, which would then send the command to the computer, and finally the output from the computer would be printed on paper again. Teletypes were continued to be used as terminals to computers until video displays became widely available in the late 1970s. Video terminals became extremely popular I/O devices on many different types of computers once manufacturers moved to a set of common standards like ASCII and 24 rows and 80 columns of text. Today, we live in a time where physical teletypes and video terminals are obsolete. We instead have terminal emulators, which are a software simulation of the real thing. But have modern terminal emulators borrowed any legacy from these old metal beasts? Let's find out. The one thing that is clearly visible is the name. If we take out T and TY from teletype, it becomes TTY, which is a prefix in the names of virtual terminals on Unix-based operating systems. The fundamental type of application that runs on a virtual terminal is a shell. The shell prompts for commands from the user and sends it for execution after they press enter, which is similar to the teletype workflow. So based on intuition, the whole thing kinda looks like this. Keyboard passes input to the terminal, which passes it to the process. The process does some work and gives output back to the terminal, which prints it on the display. But an illusion sits in between the terminal and the process. TermIOS. It's kinda like an interface to some default settings for socket communication parameters and line discipline, which affect how text is entered and printed. The manual page for TermIOS lists all these available settings. There's also the stdy utility, which can be used to turn these settings on or off. And stdy-a shows all these settings with their current values. For example, the speed of serial communication and the number of rows and columns. Let's see what some of these settings do. I'll show the same examples Brandon Rhodes shared in his 2017 North Bay Python keynote. The first setting we'll look at is called iCanon. It refers to the canonical text editor used for some rudimentary editing of commands before they are sent to the process upon pressing enter. For example, moving the cursor back and forth, or removing characters using backspace. Most interactive applications like text editors turn off iCanon and handle all the line editing themselves. The canonical text editor is on by default and we can turn it off using stdy like this. Let's see what that does. We'll open cat. And since iCanon is on, the input is buffered till we press enter. Let's turn off iCanon and use cat again. As you can see, the text is not being buffered now. Cat is receiving a character as soon as we enter it and printing it right away rather than one line at a time. We can turn iCanon back on by removing the hyphen from the earlier command. Another setting is ONLCR, where NL stands for new line and CR for carriage return. This setting finds new lines in text and adds a carriage return to each one of them. A carriage return makes sure that the cursor moves back to the first column after a new line, similar to the teletype days when the paper carriage would return to the first column with a new line. A carriage return without the new line character is used to make progress bars on modern terminals. The program updates the progress, moves the cursor back to the first column, and then overwrites the earlier progress with the new one. ONLCR is also on by default, and we can turn it off using stdy like this. We look at PS this time. The output looks very structured. But what happens when we turn off ONLCR? The illusion of structure is gone. Each line is being printed on a new line, but the cursor does not return to the first column. A lot of applications are written with this assumption that the terminal will automatically move the cursor back to the first column when they print a new line. And we can turn ONLCR back on by removing the hyphen from the earlier command again. There's also echo, which is on by default. Echo directs the terminal to print every character that we input back on the display. What happens if we turn it off? We look at cat again. We can see what we are typing. Hello, world. What happens when we turn off echo? We didn't see cat being typed in the input strings too until cat, which was running in the background, printed them for us. Programs turn off echo when they ask users for passwords. If you're experimenting with term.io settings, you can use the reset command to return all of these settings to their current values. You can also check out the term.io's module in the Python standard library to turn these settings on or off from your Python code. Another way to change a terminal state is through in-band and out-of-band signals. In-band signaling means that you throw in some special characters in your input. The terminal interprets these special characters as commands and does not print them, but it instead causes the intended effect. One way to do in-band signaling is using control characters. For example, Control-H will do a backspace and Control-C will interrupt the running process. And another way is to use escape sequences, which can control things like cursor location and text color. For example, printing the first escape sequence will clear the screen, and printing the second one before another string will make the second string bold. Terminals are also pre-configured with input and output streams, where the input stream is mapped to the keyboard and output to the display. Here, stdin is the input stream where the program reads its input data, and stdout and stderr are output streams, where the program writes its output data and error messages. Unless, of course, data is redirected using some operators. The greater than and double greater than are the redirection operators which redirect a program's output to a file. The only difference between the two is that the first one will overwrite the file, while the second one will append to the file. Another redirection operator is the pipe, which makes the output of one program the input to another. Now that we have an understanding of how the terminal evolved and how it works, let's look at programs that run inside a terminal. Command-line interfaces. The words interfaces, applications, programs, and tools are used interchangeably, but they all refer to the same thing most of the time. CLIs make it easy to automate repetitive tasks via shell scripting and are kind of fun to use. The general usage pattern of a CLI looks like this. The shell displays the prompt as a sign that it's ready to take in commands. The user then types in the command that they want to run, along with some options and some arguments, and finally ending the input by pressing the enter key. This completes the command line of text going in, hence the term command-line interface. The command is then executed and the output is printed on the terminal. But what are these arguments and options? Arguments are required items of information for a program, required in the sense that the program won't work without them. They're often positional, which means that an argument's position in the line will help the program identify the argument's type. For example, here's the copy command, which can't function without both the required arguments. The argument in the first position will always be identified as a source, and the argument in the second position will always be the destination where the source needs to be copied. An option or a flag is used to modify the operation of a command, and as the name suggests, they are optional and may have some default values. The general convention is to have hyphens in front of a character or a word to identify the option. For example, in the copy command, -r changes its operation by asking it to recursively look for files in the source and then copy them to the destination. But not all CLIs are as easy to use as the copy command. In fact, one of the criticisms of a CLI is the lack of cues to the user about the available actions, in contrast to graphical user interfaces, which usually inform the user of these actions with menus, icons, and other visual cues. To overcome this limitation, many CLIs display some brief docs around the arguments and options that they support. This documentation can be viewed by invoking the CLI with the help option. Some of them also have man pages, which is short for manual page, and it can be viewed by using the man command. Well, you must be wondering that there's a lot of moving parts here. Each programmer could write their CLI differently. For example, they could use -x instead of -h to display help text. Are there any standards to make sure every CLI follows some basic conventions? Yes, and it's called POSIX. POSIX makes APIs provided by Unix-based operating systems uniform. APIs such as command-line interfaces. To follow the POSIX standard is to be POSIX compliant. There's also the XDG-based directory spec, which dictates how CLI should store different types of files that they need for their function, so that everyone doesn't save files all over the place. These files could be configuration files, data files, or the program cache, which should go into these directories on a user's file system. Now, let's see how we can implement a command-line interface using Python. There are several options to do this, both in the standard library and on PyPI. We'll use a small example CLI called small pip and see how we can implement it using these different options. Small pip just has one subcommand called install, using which you can install a package from PyPI. It also has the upgrade option, which will upgrade the package if it's already installed, and the package name required argument to identify the package itself. Let's look at the standard library first. It has a sys module, which comes with the argv variable. Sys.argv is a list where the first element contains the name of the CLI that was invoked, and the rest of them are the command line options passed to the CLI. Internally, sys.argv uses a getOp module to pass and create this list of command line options. Let's take a look at some sys.argv code. So when the CLI is invoked, we get the list of arguments using sys.argv. And since the first element is the name of the CLI, we check what the element at index 1 is. If it is -h or -help, we print the help. And do the same for the version. Finally, we check the subcommand that was invoked and dispatch control to the relevant code. Up until Python 3.2, the standard library also had the opparse module, which has since been deprecated. Opparse could only parse options and not positional arguments, which is something that Stephen Bethard, the author of argparse, talks about it in PEP 389. This PEP proposed deprecation of opparse in the favor of the new and improved argparse module. It was approved by Guido 10 years ago on February 21, 2010. Argparse was written because both getopt and opparse support only options and not arguments. Argparse handles both, and as a result, it is able to auto-generate better help messages. Argparse also allows customization of characters that are used to identify options. For example, using a plus instead of a minus, or even forward slashes. Argparse also added support for subcommands. This is a common pattern in CLIs, for example, pip install, pip freeze, and pip search. Let's see how small pip code looks like using argparse. So we import argparse, initialize a parser object, and pass in the description of our CLI. We also add a version option to it. We then initialize a subparsers object and add a subparser for the install command, to which we add an upgrade option and a package name argument. The action is equal to store true. Make sure that the upgrade option is treated like a boolean flag. And when the CLI is invoked, we call the parser.parseArgs function, which gives us a namespace object with all the command line options as its attributes. Finally, we check the subcommand that was invoked and dispatch control to the relevant code. And like mentioned before, with argparse, we get an auto-generated help for our CLI. Now let's look at some packages that are available on PyPI. There's docop, which was written by Vladimir Keleshev, and it's kind of cool in the way it works. Docop takes a documentation first approach to writing CLIs. It just requires a POSIX compliant help string as an input, from which it'll infer subcommands, options, and arguments on its own. So this time around, we first create a help string which shows our CLI's description and usage. And when the CLI is invoked, we call docop, pass in the help string and a version, and it returns a dictionary of the parsed command line options. We again check the subcommand that was invoked and dispatch control to the relevant code. In all the examples till now, we saw that in addition to parsing results, we also had to write some boilerplate to dispatch control to the relevant install and upgrade code. If we had to validate the parsed command line options, we would need to add some more boilerplate. This boilerplate can grow real big for large applications. There might also be some common features that we might want to add, like progress bars and colors, for which we would usually need to install more packages. Now let's look at Click, which was written by Armin Onaher to support the Flask project. Click automatically dispatches control to the relevant code based on the subcommand that is invoked. It supports callbacks, which can be used to validate past command line options, and it's POSIX compliant. Let's see what small pip looks like using Click. So we import Click, add a function called CLI with a docstring, and since Click follows a decorator-based approach to writing CLIs, we add a click.group decorator to the function. It makes the function a command group to which more subcommands can be added. We also add a version option using the click decorator of the same name. And then we define a function called install with a docstring again. This function will contain the code required to install or upgrade a package. We then convert this function into a subcommand using the CLI.command decorator. The CLI in CLI.command is a command group that we defined earlier. We then add an option called upgrade along with the help string using the click.option decorator. The is flag is equal to true makes upgrade a boolean flag, similar to the action is equal to store true that we saw in argparse earlier. Finally, we add a package name argument using the click.argument decorator. And when the CLI is invoked, Click will automatically dispatch control to the relevant code, which in this case is the install function. We will get the arguments and options as keyword arguments to the install function, which we can then use to install or upgrade a package. Click also auto-generates a help for a CLI based on the function doc strings and the option help strings that we added. Click promises that when multiple apps written using Click are strung together, they will work seamlessly, which means that multiple people can work on different parts of a large CLI and stitch all of them together at the end. The Click way of building a CLI where we don't have to define parsers from the start or focus on our help text from the start is also great for quick iterations. Now let's look at some common use cases and see how we can use Click to implement them. We'll use another small example CLI called small-get. Small-get, as the name suggests, is a small-get clone with 6 get subcommands: clone, config, log, status, commit, and push. So we define a CLI function with the click.group decorator, and let's jump into the use cases now. A common CLI use case is to display progress bars to the user. For example, we should let the user know about the progress of how many files have been cloned when they invoke the clone subcommand. Click has a progress bar utility that can help us do this. So we first define the clone subcommand with the source and destination arguments. And then let's say we have a list of files that we want to clone. We can pass that list to the click.progressbar context manager, which returns an iterator. And as we iterate on it and download each file, Click will show the user a progress bar, which looks like this. So I invoke the clone subcommand with the repo that I want to clone, and I get to see a progress bar as each file is being downloaded. Another use case is to persist user-specific configuration to a file. For example, we should persist things like username and email in our application folder when the user sets them using the config subcommand. Click provides a function which can help us do this. So we start by defining a config subcommand with the key and value arguments. We then get the application folder path for small-get using the get_appdir function. We create the path if it does not exist, and finally store user-specific config settings in a file called config. Using the get_appdir function, make sure that our CLI follows the XDG spec. And since the function is cross-platform, it will return the most appropriate path on Windows, macOS, or Linux. And look, it looks like this. I do a small-get config, set my user.name to Vinayak. And if I do a cat on the config file in the application folder for small-get, I can see that my username is set. We should also page large CLI outputs so that the user can scroll through it instead of printing it all at once. We should do this for the large commit log that the log subcommand prints. Click supports paged output by calling a terminal pager program like more or less. So we define a log subcommand where we can use the click.echo via pager function to display the large log string. And it looks like this. I do a small get log and I can see and scroll through all the commits in the log. We should also highlight the file names that are added or modified using colors when they are printed using the status subcommand. Click can help us add color to text. It uses a Colorama package underneath to do that. And Colorama in turn adds escape sequences to text to color it, as we saw earlier. And to do this, we define a status subcommand. Let's say we have a list of files and their status. We can use the click.style function to add a foreground color and even make the string bold. Finally, we output it using the click.echo function. The nice thing here is that Click will auto strip escape sequences if the output is redirected to a file. Because when we do that, we would not want to look at incomprehensible escape sequences. And it looks like this. I do a small get status and I can see that a new file called a.txt has been added since it's highlighted using the green color. Sometimes we might also want to get multi-line input from the user. For example, asking the user for a commit message when they invoke the commit subcommand. Click supports launching editors for this use case. It will automatically open the user's default editor or fall back to a sensible default. So we define a commit subcommand with a message option. And if the user doesn't use the message option when this subcommand is invoked, we launch an editor to get the commit message. And it looks like this. I do a small get commit. And in this case, it opens Vim, which is my default editor. I put in the commit message, save it, and it gets committed to the log. We can also ask users for one-line input using the click.prompt function. This can be useful for the push subcommand to ask users for credentials to push files to a remote repo. So we define a push subcommand with two arguments, the remote repo we want to push to and the local branch that we want to push. And then we use the click.prompt function to ask the user for their username and password. Here the return values will be stored in the username and password variables. And notice that for the password prompt, we've set hide input is equal to true, which won't print what the user types on the terminal. Internally, Click uses a getPass module from the standard library to do this. In getPass, turns the echo setting off using the term-ios module while the password is being entered. And it looks like this. I do a small git push origin master, enter my username, my password, but you can't see it, and all the files get pushed to the remote repo. And we are done. We have a small git CLI with the help auto-generated. Click also lets us test the CLIs that we write. We can use the CLI runner class to invoke each subcommand in our CLI and check the result against their expected output. And these are only a subset of features which Click has to offer. You should totally check out the Click docs to look at more awesome things that you can do with Click. Finally, let's package smallgit. To do this, we just create a setter.py outside the smallgit module and add a console scripts entry point to it. Console scripts allow Python functions to be registered as command line programs. You can check out the code for smallgit on the GitHub link in the resources. And once we package our CLI, we can also push it to PyPI so that other people can install and use it. And to do this, we create a source distribution and a wheel using the setup.py and upload them to PyPI using Twine. Now that we know how to write CLIs in Python, let's briefly talk about the CLI user experience. As mentioned earlier, we are operating in a constrained design space in contrast to graphical user interfaces, which offer a lot of visual cues and guidance to the user. There are some principles that can help us create a nice UX for the CLIs that we write. The first one is to keep things simple and follow the Unix philosophy of doing one thing and doing it well. Writing programs so that they can work together using the redirection operators and handling text streams. Following the Unix philosophy makes sure that there are no surprises when users interact with the CLIs. And the second is to make features discoverable by being forthcoming about them. Kinda similar to the cues that the graphical interfaces offer. Some things that can let us do that are storing a user's command history as a user CLI and letting them search through it by maybe giving them a search interface or auto-completions based on that history. Amjit Ramanujam talks about this in detail in his PyCon 2017 talk, which you can find in the resources. He also talks about Prompt Toolkit, which is a package written by Jonathan Slenders, and it can help you implement some of the history and auto-completion features we just talked about, and also do a lot of other things. It's used by IPython in all the DB CLI tools. Finally, we are at the end of our CLI journey. I hope you got a lot of touch points through the CLI ecosystem that you can now explore further. I hope you also get an understanding of how terminals in CLIs work and how to write CLIs using Python. This slide contains links to some resources mentioned throughout the talk, and the slides are themselves available at the first link. If you have any questions, you can reach out to me on Twitter at vortex_ape or using the contact information on my website. I also want to give a huge thank you to the PyConline AU team for everything they've done to bring this conference online. They absolutely deserve your thanks as well. So be sure to let them know that you appreciate all the hard work they are doing. See you all next year.